Hello, welcome back my friends to lecture number 19. So today we'll be having the last lecture of chapter 4, and in this lecture we will go through some of the uh, properties of Hermitian operator that we have not focused it earlier. Okay, so let's resume the discussion exactly from the point where we left last time. So we have been discussing about the condition for an operator to behave as a Hermitian operator. So this is the condition, and that we have discussed already earlier. Here we can write an alternate statement. Okay, so this is in terms of f and d tau. So in alternately we can write that in terms of psi as a function of x and dx. So if you ever find a statement like this, so please don't get confused, because it says the same thing as the condition of the Hermitian operator. Okay, so things will look like this. Okay, so this is basically an alternate statement. So look at here. So this operator A is operating on F, so A star on F star, so A psi star, and then we have taken that F as psi outside. So this, the right hand side should be equal to the left hand side, like I wrote here. Okay, so this is an alternate statement. So now remember what we have been doing last time. So we have been doing some practicing, right? So as a practice exercise, we took up that we saw that ddx, the operator a cap is ddx, is not a Hermitian operator, definitely. All right, so now the question is, I think I have asked you to solve it, to try whether a cap is equal to minus IH cross ddx. All right, so you know it very well that this is the momentum operator in x direction. Whether is this a Hermitian operator? Okay, so that is the question now. All right, is the question. So can we solve this? All right, so I think I will give you a hint once again. I hope following the hint you will be able to solve the next operator that I'm going to give you. All right, so let's try it out here. All right, so we start it again. So this is what we have to prove, and our operator is minus h cross ddx. So if we go from the left hand side, so we get integral f star, here a is my minus ih cross ddx, and it is getting operated on f, okay, dx. All right, so what I can do now, that I can take that minus ih cross outside, so or I can take this minus ih cross and I have f star. So here we have ddx of f dx, so simply we can write it as df. All right, so here this is simply we can take that as a integral u dv, so we can directly apply the integration by parts formula. All right, and if we do that, and if we put the limits, so here the limits are actually limits minus infinity to plus infinity, because as I have already told you that if nothing is mentioned, then by default we can take it the limit as minus infinity to plus infinity. So now if we apply the integration by parts on this, so what we have is this. So here I have skipped a step. All right, I have skipped a step, and here the LHS should look like this. All right, so now let's work it on the right hand side, RHS. So the RHS is equal to here f, and we have minus IH cross ddx, and this is whole under complex conjugate, means star, and then we have f star dx. All right, so what I'm going to do is I have to take the complex conjugate of IH cross minus IH cross. So if I do that, so H cross is equal to H cross star is equal to H cross, and this minus I star means plus I. So I H cross would come outside, and inside we have F, and ddx star is actually ddx, so ddx, and we have f star dx. All right, so now which we can write further as IH cross, and again minus infinity to plus infinity, the same thing, because if nothing is mentioned we can take this default limit f, so this transform into this. So now you see this is LHS, and this is RHS. So here the left hand side is equal to right hand side, so PX is Hermitian. All right, so very simply we have proved it. Okay, so now if you have understood this process, how we approach, it is your job to prove. So I am giving you as a home assignment, it is your job to verify that minus h cross square divided by 2m d2 dx2 is a Hermitian operator. All right, so yes, you got it. This is nothing but the momentum energy of kinetic, the kinetic energy operator. So this is nothing but the kinetic energy. Yes, the kinetic energy operator. So we have to prove that this is a Hermitian operator. All right, so you can try this approach or any other approach that you like, but finally you have to prove it. All right, so now this is not the all though. So for all our commonly known operators, for we have to do the same thing. All right, so that means we have to prove that the position operator x cap, so we can write here position operator x cap, okay, potential operator, potential energy operator Vx cap, etc., and Hamiltonian operator, okay, means the total energy operator. These all uh, operators correspond to uh, uh, physically measurable quantities. All right, so to the knowledge that we have already seen, according to that knowledge, these operators should act as Hermitian operators. So our job is to verify whether uh, these operators along with this one kinetic energy operator are all Hermitian operator. All right, so you please go ahead and try it out. All right, so let's quickly move on to the next or the last topic, that is we will be talking about a very special property, a special property of Hermitian operator. Okay, so let's take a look. Okay friends, before we proceed further, I would like to tell you that there exists a more general definition of Hermitian operator, and it states like this. So integral g star a cap f dt d tau is equal to integration f a cap star g star d tau. So here you see previously both side there was f, so means a function and its complex conjugate, but here you see f and g may not be identical, but yet if they satisfy this condition, where of course g and f are well behaved, then we can still say that the operator a is a Hermitian operator. So now, what kind of functions or what kind of relationships can G and F have? All right. So for that, we proceed to the very last property that we are going to discuss on Hermitian operator. Okay. So the application of this statement you will find out to the next step. So here we begin with another statement. So the statement says the eigenfunctions of a Hermitian operator are orthogonal for non-degenerate systems. All right. So here it says the eigenfunctions of Hermitian operator. So that means a Hermitian operator may have more than one eigenfunction. All right. So how is it possible to have more than one eigenfunctions? Of course, we have seen in a free particle in one-dimensional box where we have many eigen values for a Hamiltonian operator, and those values are defined by an integer n. Okay, so here, so let's assume that psi m and psi n are both normalized. All right, so that means it automatically tells that they are well behaved, and A is an operator which is Hermitian. Okay, so that is our assumption we begin with. So here, if before we apply the condition of Hermitian operator, since psi m and psi n are both normalized, and A is a Hermitian operator that can operate on psi m and psi n and can produce two different eigenvalues. So in that case, we can definitely write that A cap psi n is equal to A n psi n, where A n is the eigenvalue of this operator A cap. Also, following the same relationship, we can write A cap psi m is equal to A m psi m. All right, good. So here you see, you can think about the particle in a box problem. So these two equations we can very well write there. So we are not writing anything very unheard of or unseen by you. Okay, so you are already very familiar with this type of expressions. All right, so now what I'm going to do is, since A is a Hermitian operator, I am going to apply the condition of the Hermitian operator. So which condition I'm going to write? I'm going to write exactly this equation. All right, or I'm going to apply this condition. So that means here my G and F are different. All right, so here instead of writing psi n star A cap psi n, I'm going to write, or since A is Hermitian, I can write that integral psi, I can take psi m star A cap psi n is equal to integral psi m star A n psi n. All right, so I have just applied this condition here for this set. And also, so what I can do is I can take this thing and all right, so I can write this one, or I can make it simplified manner. So I can take that an out, okay, because it is already an eigenvalue. So this reduces to something like this. So of course I have to write dx here, that I have forgot to write it. Okay, so this is the one I have. Now I call it equation number 1. All right, now we take this equation and again we apply the condition of Hermitian operator on this equation. So, or we can write integral psi n star a cap psi m is equal dx, sorry, is equal to then we have psi n star am psi m is equal to, I can take am out, all right, yeah, actually, so sorry about that, I just wrote a wrong step. So let's consider it an equation 1, and then I'm going to write an equation number 2, but since there is not much space and I want to clear that rightly over here, so I'm just clearing the board and I'm writing it here freshly over there. Okay, sorry about the confusion. So let's make things a little bit more clear. So this was the equation that I wrote last time. This was our equation number 1. So now what are we trying to do this here? So this was the condition for Hermitian operator, and we have two eigenvalue equations, right? One is this in terms of psi n, and another this terms of in terms of psi m. So now we can think that our function f may be psi n and function g may be psi m, because now these two are different. So f and f star, so this is not the condition of f and f star, but this is a condition of f star and g or g star. Okay, so if a is a Hermitian operator, we must prove this, means a must fulfill this condition. What's the condition? That psi m star, so I can exactly translate this condition into here. Psi m star a psi n dx is equal to psi n s star a cap star psi m star dx. So instead of f we have put psi m, and instead of g we have put psi n. So if this is true, then this is my LHS and this is my RHS, so LHS has to be RHS. So whatever equation 1 we got earlier, this is exactly my LHS. Okay, so now what would be my RHS? So RHS exactly should be is equal to integral psi n a cap star psi m star dx is equal to, so now I can write further exactly like this. This is a psi m a cap whole star dx, and now a psi m is equal to a m psi m, so I can write psi n a m psi m whole star dx. All right, so here we can further write that we can take a m star out, integral psi n psi m star dx. All right, or we can rearrange this a little bit and we can write a m star psi m star psi n dx. All right, so this would be my equation number 2. So this is equation number 1 and this is equation number 2. So what I'm going to do this next is I want to subtract equation number 1, or I can want to subtract equation number 2 from equation number 1. All right, so I just have to erase the board here, so please bear with me. Okay, so resuming over whatever we have just wrote previously, equation number 1 and equation number 2. So we have just subtracted equation 2 from equation 1. So I have written subtracting, we get this expression. All right, so this is the basically condition for Hermitian operator is equal to this. So now we have already settled that since A is a Hermitian operator, and for that to be satisfied, this portion should be equal to that portion. And needless to mention, there's all the limits here are from minus infinity to plus infinity, but I'm not writing it. So, or since this part becomes 0, so we can write that an minus am star multiplied by psi m star psi n dx is equal to 0. Okay, because this left hand part is 0 due to the fulfillment of Hermitian operator. So now for this entire thing to become 0, so we can call it our equation number 3. So for equation 3 to be 0, there are certain conditions to be fulfilled. So there are two possible scenarios. Okay, so we can write that there are two possibilities. Okay, so what are the possibilities? So possibility number 1. Okay, the possibility number 1 says that if n is equal to m. All right, so if n is equal to m, then what we are going to have, that we can write an minus an star, okay, integral psi m star psi n dx is equal to 0. Sorry, m is equal to n means we have to replace m with respect to n. All right, very good. Yes. So what would happen here? Okay, so here definitely this part will become is equal to this value. Then since this is a well-behaved function, okay, so this part, okay, psi n star psi n, so this part will always be equal to 1. All right, because this is well-behaved function. So then what would happen to this part? All right, so excuse me, there is a phone call coming, so I'm pausing it and I'll be back. Yeah, thank you, I'm back. So as we were discussing, so this is the equation number 3, and we have found out that the equation 3 is equal to 0. Now the outcome, that is for equation 3 to be 0, then it would create two possibilities. Okay, so there are two possibilities that would satisfy when equation 3 is equal to 0, and the two possibilities are, so the first possibility, if m is equal to n, all right, then what would happen is, I am writing it once again, an minus an star integral psi n star psi n dx is equal to 0. All right, now in that case, that we knew that since psi n is a well-behaved normalized function, so psi n star psi n dx, so that is the total probability. So the total probability is finite is equal to 1. So that means this part is not is equal to 0, but for the entire equation 3 has to be 0. If this part is not is equal to 0, then this part, that is an minus an star, it has to be 0. Now if it is 0, then obviously an is equal to an star. So that means what? So that means the eigenvalue or eigenvalues are real. Okay, so that means whenever we have m is equal to n, then equation 3 would give you 0, based on a very simple assumption or the postulate that we have already seen, the eigenvalues are real. Okay, so for m is equal to n is a rather simpler or rather familiar conditions for us. Now we would discuss about the possibility number 2. So the possibility number 2 is that what if m is not equal to n. All right, so then what happens, that I have a n minus am star multiplied by psi m star psi n dx is equal to 0. Now since m is not equal to n, so that means here an is not equal to am star, so that means it cannot be 0. So definitely this is a non-zero quantity, so this cannot be 0. So that means whatever we have, this part psi m star psi n dx is equal to 0. So whenever this condition is fulfilled, that is that for two non-degenerate eigenfunctions, remember psi m and psi n are two non-degenerate eigenfunctions, when complex conjugate of one multiplied by other, integration over the whole limit dx is equal to 0, then we call that, psi m and psi n are orthogonal. Okay, so these are called orthogonal functions. So this actually is, now we have proved that the initial statement that we have written, that the eigenvalues of the Hermitian operators are orthogonal. So what are the eigenvalues? For psi m it has the eigenvalue am, and for psi n it has the eigenvalue an. So now we can tell, since these two functions, eigenfunctions, are orthogonal, so their eigenvalues are also orthogonal. All right, so now we can put the entire condition, whatever we have discussed, by one single expression, and we are going to generalize it. So let's clean the board and let's write the generalized treatment. All right, so during the very last thing that I mentioned, I made a small mistake. So actually eigenvalues have to be, sorry, the eigenfunctions have to be orthogonal, not eigenvalues. So probably I said that eigenvalues are orthogonal, but please correct my statement. So the original statement was the eigenfunctions of Hamiltonian operators are orthogonal, and we have shown that psi m star and psi n, if those are orthogonal, then in their multiplied the integration psi m star psi n dx should be equal to 0. So that is the condition for orthogonality of eigenfunctions. So here we learn a new term, orthonormality. So this is nothing but the wave functions that are orthogonal and normalized, those condition is called, that condition particularly is called the condition for orthonormality. So that means two wave functions, psi m and psi n, those are orthogonal provided they are normalized, then we call it they are orthonormal. So orthonormal and orthogonal are pretty similar terms. So now we have we will be writing a generalized condition for orthonormality. So for orthonormality, or the condition for orthogonality, the same thing. So we have minus infinity to plus infinity, psi star j psi I d tau. Okay, so this integral is equal to, this is expressed as the outcome as delta ji. All right, so now we can write that delta ji is equal to 0, okay, if j is equal to I, and delta ji is equal to if delta ji is equal to 0 if j not equal to I, and delta ji is equal to 1 if j is equal to I. All right, so this delta has a name, it's called Kronecker Delta. Okay, so this is known as Kronecker Delta. So simply by finding out the value of the Kronecker delta, we can tell whether the two functions psi j and psi I are orthogonal or not. All right, so this is the condition. Once again, this is simple, that if j is equal to I, it becomes the total probability, isn't it? Psi star psi d tau is equal to 1 if both are equal. But if I is equal to not j and then it delta ji becomes 0, they are orthogonal. If this is a non-zero, then they are not orthogonal. Okay, so this is this special property of the Hamiltonian operator. So now you have to prove that the eigenfunctions of particle in a box, okay, are orthogonal. All right, so you take the example of this psi m and psi n of particle in a box and you prove that those are orthogonal. All right, so that's your task. So I think we are finished with chapter 4, so it is time for do some more exercises. So we will do that before we go into chapter 5. All right, so you please study this video minutely and start doing the exercise problems. All right, so see you later. Goodbye.